So step 4, we're going to be converting the BGEN file to a bed file. So it's a plink1 binary format. So going from the BGEN and the BGI files and using the dot sample information to come up with the bed, BIM, and FAM files. Those are plink1 binary format files. So in the process, we'll be running bash step 4, create bed file all chromosomes.sh. So just for those 11 chromosomes that we were using for our score information in this case, but this is what will be what we're running in step 4. So yeah, we're going to be using the plink2 tool to convert the BGEN files to the plink1 format binary files here. So what you see here, the binary formats, we have the .fam file, the .bed, contains the binary version of the SNP info. It's not in a format readable for humans. It's kind of like alien language a bit. And the BIM file here, like what are the variants that were extracted. So what you see over here is in this plink2 command that we'll be using, plink2 BGEN, file.bgen, ref first sample, file.sample, make bed out prefix. Ref first is going to tell plink2 that in the BGEN files, the first allele is listed as the reference allele, which is usually the UK Biobank convention. So that's important to note. And so this ensures that the allele alignment is correct. So when it's guessing, like, is it the reference, is it the alternate, right? And the sample file.sample, it provides the sample IDs, like the gender, the missingness information that is required for the BGEN. And the make bed converts the BGEN to Plink's binary format. So the bed file, the BIM file, and the FAM trio. So it's a trio, 3 musketeers. And the out prefix is going to give the out prefix for the files. Like, what are these files altogether going to be? Because they'll have the same prefix. So it'll be prefix.out prefix.bim, out prefix.bed, out prefix.fam. So what is that? So this is the code that we're going to run to create the bed file and BIM and BAM file from the subset BGEN files. This is the code. So it converts the extracted BGEN files for chromosomes 1 to 22, based on if they're found or not, to the plink bed format using plink2 with the correct ref first flag. So this is after we've created the filtered BGEN files, based on the PGS catalog SNPs. In this case. So in UK Biobank, again, the reference is always listed first, so we use ref first. For instance, if we have this format here, where you see the T and the C, the first allele, the reference allele from GRCH37, this is the T, that's the reference, and then the alternate allele will be C. So the first allele will be the T, which is reference, and then this was alternate. And then this will be matches the UK Biobank convention, because the reference is always listed first in that. So make sure you check if you're doing this for anything else in general, how you do that. And then as we run this code, so similar to the third step, what we're trying to do is, so we're running a loop, so from chromosomes 1 to 22. And again, there could be other more efficient ways to do this. This is just how I'm doing it. So feel free to, give any feedback as well. But here, this is the same defensive step where we're going through all 22 chromosomes. I could have listed out the chromosomes, like for CHR, one and all of the different ones, but I want to make this dynamic so that because different score files will have different chromosomes that they could have scores for. So this is just dynamically checking, and now we're checking that if the BGEN file exists. So it's the BGEN directory here that we have, the one we're working with, the subset BGEN. It's found in the extracted genotypes BGEN, what will be created in the third step. It's checking in this folder, that's the BGEN directory, if the BGEN file name. The BGEN file name is that file name prefix.bgen. The file name prefix is going to be this PGS ID here, the genome build UKB 228828 subset, this one, the one that we just created. You see over here, this is what these files look like here. And we're focused that if the BGEN file exists, the .bgen. And of course, if the BGEN exists, then the .bgi will also exist because it's an indexing file for the BGEN. But it's checking, we have for the 11 chromosomes. This is 22 because I was just filtering for BGEN. So we have a BGEN and BGI. So 11 times 2. 22 here. But anyways, it's searching if the BGEN file exists. If not, then it says that the filtered BGEN file for that chromosome is not found. It's skipping for the, for the bed file. It's not going to be running plink2 otherwise. And then this one is going to be running the plink2 command otherwise. And we're going to be outputting our results in this destination, this output folder, which will be Sanya tutorials extracted genotypes _bed. That's where it will go. And we are going to be uploading here the BGEN directory, BGEN file name. So we're going to be bringing this BGEN file name here and the sample directory, sample file name. So this is the sample directory, the UKB imputation from genotype, and the sample file name, which will be the .sample. And again, we need the absolute file names here. We need to know where those files are located. When we're mentioning the BGEN file name up here, we need to know where this came from. This is coming from the extracted genotypes.bgen, which is in Sanya tutorials. That's what we're saying, that when we mention it, this BGEN file name was found there. When I'm mentioning sample file name, I really want you to upload it from sample.dir here. And when I'm mentioning the output folder, I need you to be very specific and tell me exactly where you want this output to be, this output prefix file to be saved. And this extract command is run over here. That's what the ICMD is doing. So it's using the plink2 tool, using the Swiss Army knife, as you see here. So what you see here is we are creating a plink1 binary file set, like plinkton. So if we look at the plink2 in the data information, so plink2 BGEN input, this kind of thing, for instance, what it's doing is that the make bed creates a plink1 binary file set. So that's what we're going to be doing. The plink1 binary file set, the BIM, the FAM, and the bed. It makes its bed with that one, trio. So now in step 4, we're going to be working with this new subset BGEN files that we have, and the BGI files, the indexing files for the BGENs. And we're going to convert those for each of those 11 chromosomes. We're going to convert those to the plink1 format files, the bed, BIM, and FAM files that we need. So to do that, we're going to see that here we're working with this folder. Now, no more the UKB imputation from genotype files because we've subset these. These are tinier. You can see how, like, just, bytes, not like giant gigabytes, just small little bite-sized files that we can work with. So we're going to go here and we're going to go to the step 4. And what we're doing is we're going to be going through each of the chromosomes, and if the BGEN file is not found for that chromosome, because we only have it for 11 chromosomes. So this BGEN file DX is this BGEN directory, which is the extracted genotypes BGEN. That's what this is. The Sanya tutorials, we start here. Extracted genotypes BGEN. And what the name of the BGEN file name will be, the file name prefix, which is this PGS ID, which would be, the file prefix would be this ID, which will be the PGS 00053. Then the genome build, which is GRCH37. Then the UKB22828 subset. And then CHR, and then let's just say chromosome 1. So wherever the $sign and the brackets are, like that just is a placeholder that you put the variable name in. So when chromosome 1, CHR is 1, right? So CHR 1, and then the RSIDs. That's what the prefix is. So it's going to be searching. So this is if CHR equals 1. In this case, then this PGS ID comes from here. You just pluck this in here. That's what this guy here is. And then this GRCH37 comes from this genome build here is the variable. And there should not be any spaces between the name and the variable in bash. Otherwise, it'll give you a warning or an error. It won't work. It cannot have any spaces. It's just like in Python, like how you can't it's very tabs sensitive and whatnot, like for indents and stuff. So it's going to see if this file exists because this is the name of, for a given chromosome, this is the format of it. The PGS, GICH, UK Biobank extracted SNPs, this .txt, that's what it is. So if that file, if it's null, that means that file does not exist. It's listing it and trying to see, does that file exist in this directory, in this folder? And if it doesn't, that means that that chromosome does not have any score files, so we should just skip it and not do the conversion. And just a quick check because I could have hard coded for chromosomes in 1, 2, 4, I could have hard coded the chromosomes, but I want to make this that it can apply for all sorts of cases for your data, my different traits and so on. So that's why I'm doing it this way. And then we're going to be running the plink2 command. If that BGEN file, that subset file exists in that folder, in this folder here, then we're going to be running the plink2 command on it. And we're going to be making that BGEN file into a bed file, and then also outputting with it files that begin the same essentially, but it's going to be a bed, BIM, and FAM files. So that's what this is going to do here. It's going to submit this job here. And again, we're uploading the BGEN file. We're uploading this subset file as BGEN file name that has come from the extracted genotype. So for that chromosome, we are uploading that file name, and we're also uploading the sample. So the sample information remains the same. Only thing we have done, all we did is we just have subset the BGEN file for this set of SNPs. We have retained all the samples so far. We've retained those samples that we have genotype information, the participants, the humans. We've retained that. We have not filtered it. So the sample file would be the same as the original file. So what we're doing right now is we are just going to be using the sample files that are located here in the imputation. Let me show you here. We're going to be using these sample files in imputation. We'll be using these sample files for the corresponding chromosomes. That's what we'll be using. We'll be uploading this. And that's what we mentioned here. We'll be using the samples because it needs the sample information here. So the sample directory is the bulk imputation UKB imputation from genotype. So you note that we don't have to mention this IBD project SANIA part in front. We don't need to do that. It just needs to start off from the current folder. So bulk is where it is. SANIA tutorials is this other folder. So we just need to do this. And again, this is the local file name here. And this sample file name is the local sample name here for that chromosome. So for chromosome 1, for instance, it would be, this is what it would look like, which is what this is here. You'd put C1. And what you notice that when we are uploading it for sample file name, we're giving the sample directory, we're giving the complete directory here in the DNAnexus job. So it knows where those files are. So it can upload those into the environment when it's running this job. So now I'll show you how we run it. And right now, just to clear up all of this, I'm going to do ls. Oh, X, ls. I'm going to do bash step 4, create bed file allchrome.sh. So it's doing this converting BGEN to bed for chromosome 1, for chromosome 2, chromosome 3. So it's skipping it for chromosome 3, for skipping it for chromosome 4 as expected. It's doing it for chromosome 5. So you can see where it's skipping it for like 9, 10. It's going through this as expected. And each of them is having its job whenever it's able to submit it. You can see the echo is what's being printed, right? Like it's printing it out, like submitted link conversion job for chromosome 19 here. There's a little smiley submitting the job. So that's what's being printed to the console. So now you can see these are the other jobs, the PGS extract parts. Now this is BGEN to bed. And that's the tag that I put here. That's what this tag is saying, BGEN to bed, and then the chromosome CHR. That's just telling me that for chromosome 1, and this is the command it's running, extract command ICMD. So for a given chromosome, it'll be like chromosome 1 will be this one here. So it's just waiting, and then it's going to be running them for these 11. So this was the previous one we just finished. Now this is this new one, converting the BGEN to the bed files. And what we will notice is that I'm going to be putting the new outputs in extracted genotypes bed. Right now, that folder does not exist, but I'm going to be creating it. And I know I could have done this in the simple starter example. I could have put them here, those folders. But I just sort of wanted to show you, again, how we can also just still do this in this job, just to spice it up a bit. And you'll notice that now that it's starting, it's created this bed. It's empty right now, but it's starting this process. It's waiting, and I've given it like a high priority so that it runs a bit faster. I mean, it may cost a little bit more, but just so it runs more efficiently. So yes, let's see what happens now. So for instance, for chromosome 2, what we will see is that, we had these extracted SNPs here, these 2 files here that we had, and we had extracted them and saved them in this .bgen.bgi, the index file, and the BGEN file here, and it was filtered for the SNPs of interest, which were these 2. In the previous step 3, we had filtered them. The initial UK Biobank, the genotype data, we had filtered them for the SNPs of interest. And so this is what we're using for the inputs, the BGEN file and the indexed file. And we also have the sample, the .dot sample. So this is the original sample file for chromosome 2. Because we did not do any subsetting for the chromosome, for the given chromosome, we did not do any subsetting by the samples. So we kept all the original samples that we had the data for. So that's why over here, we're just using the original UKB imputation from genotype dot sample. So these are the inputs that are going in, and we're using the dot sample and then the BGEN information. We're using that, and we are supplying that to the plink command in order to create the bed file, the BIM file, and the FAM files. So we're going to be running the job for chromosome 2 here. And as you see here, it finds these 2 variants in the header, those 2 ones that we had found for chromosome 2. These number of samples imported from the dot sample file, so many females, males, ambiguous. And again, your numbers may differ based on your UK Biobank project and information, but it should be in the ballpark of around 500,000 samples as of now. So then ultimately it says that writing this .fam done, .bim done, and .bed done. So then it's uploading them to the output directory that I've given. So it says home, DNAnexus, out. And this out is what folder we've given. But internally, it's read as that code. It's a destination that we'd given when we run the DNAnexus dx run command. It's outputting the log file, the FAM, the bed, the BIM files to that area. So you see here, the input ones that we were using are the BGEN files and the dot sample. And here it didn't use the indexing file because it's just converting from one to the next. When we were doing the subsetting using the BGENX, it needed the index files. But here, because we're just kind of converting an existing BGEN file to the sample, and the sample to those formats, it doesn't need to use any indexing because it's not subsetting anything anymore. It's just taking the file and then converting it to a different format. So it doesn't need the indexing file. So it just takes the BGEN file and then the dot sample. So for chromosome 2, this is what it's reading in its command. It's figured out the BGEN file and the dot sample. And then its output the log, the fam, the bim, and the bed files for that chromosome. That's the out. And this is the in, and this is the command that was run. And that's how much it costs. So what you see here for chromosome 2 is going to output the fam, the log, the bed, and the bim files for it here. In this output directory, the files are in the extracted genotypes bed folder. In Signing Tutorials in the extracted genotypes bed, I'm just filtering for CHI2, so I find these 4 files there. Oh, now let's see the status update of this job that we've run. Let's see how that's been going and if it's finished. Okay, so let's just see this here. We see is now, yay, this job has finished for these 11 chromosomes that, in our score file, it has finished converting the BGEN to a bed file. Yay! Woo! Okay, so let's just see what, for example, like what this looks like. Let's just go on in and see here, for example, for this one. What we've seen took around 2 minutes is more efficient. It's just a very quick computation. So over here, what we had specified here, and you see this, okay, is that we'd given these 2 files to be uploaded, and these are the same 2 files here that we will find over here. And then we noticed that the first one is the BGEN, and the second one is the sample. And we've given the information for how those can be uploaded, where those locations are, where the BGEN directory is the extracted genotypes BGEN, that filtered file. And this sample directory is the original samples. I mean, because it's the same, we didn't filter any of the samples when we were subsetting the BGEN file. We kept the samples the same, so we can just use the original again. If we had subset the samples, we would probably be using like extracted genotypes BGEN sample. We'd have done something differently in the step 3. So now this is the command that has been run for chromosome 1. This is the plink command. So let me zoom out a bit. This is the plink2 BGEN. We have the BGEN file name here. We have the ref first. This just means that the reference is always listed first here. So like if we have, if this is what our BGEN files look like here, that this T is the reference allele and the C is the alternate allele here. Like if this is what our BGEN file is looking like, the variant information, RSID, chromosome number, position, and so on. And then this is the sample here, and this is the sample information, which is what the sample file name is. Then we have our make bed here, which is what this is over here. Then we have the out. And then the out is just using the same heading, the file name prefix, the same thing here, this file name prefix. I just wanted to be the same. So how it was reading as the BGEN here, I just want the outputs to be all sharing this same information here. I want all the outputs to have this as part of them. So I want all the outputs to have this in the stem. Oh, eeks. This in the stem of the name. That's what this is here. And so on. And we have the outputs. We have the log file, the fam, the bim, and the bed files here. That's what it is. That's what you see here. And so for instance, and that's what the command is saying. So we'll have this log file. And this log file will basically show us. And this again, guys, this is just really dependent on your UK Biobank data. So this is just for mine. Please don't worry if your numbers are different. If you're following along and trying to do this example with me, it may differ based on your project information and so on. So a random number, this is when I was running it from the UK. This is the information here. We've got so many samples. This is what I have. So many females, so many males, so many, we don't know what the gender is. Many founders here. This number is same as the samples. And these all add up to the samples here. And then what it's doing is it's found this one variant for chromosome 1. Remember, like in the subset file, we just had one variant that we were wanting for this chromosome 1. This just had, in the get info, this just has this one variant, right? So that's what that's kind of alluding to, that just one variant was loaded from this. So it's created the FAM, BIM, and BED files here for chromosome 1. We have the FAM here. You see over here, we have the BIM. Just telling you about this one variant, that the same variant that we were wanting, the same guy here. And we also have the BED file. I also recommend being careful about what you can download given the permissions for UK Biobank. Please be mindful of that. So here you can also see this is for chromosome 20. Everything is chromosome 20 specific. And we also have the log file. This log file is going to tell us that, for this chromosome, again, we just found one variant and we've got the corresponding files here. I remember that like for chromosome 14, we had a few variants. So let me just show you that example here. So in the log file, this log is kind of like all the processes that we did. Again, just the same number of samples. It's just the same, the sample files. It has these two variants loaded from it. And for chromosome 14, we have these two variants. And I recommend just double checking that you find all the variants that you needed. We found those two variants from that. And in fact, just to show you that that's what was also picked up, we have the BIM file here. Just these two variants over here for chromosome 14. And so on. So that's what we were seeing for all these different runs, chromosome 11 here for the log file. 4 variants over here were found. Again, the samples are the same. And that's the log file is saying what was happening. We have the BIM file, we've got the FAM. And these are the 4 variants that we'd picked up. And you can see that all of these are chromosome 11 specific. Chromosome 11, and these were the 2. Because that's what we're doing in the loop. We're going through each of the chromosomes and seeing if they do have this BGEN file in that folder and the extracted genotypes BGEN, and then we're putting them in the BED folder. So let me show you now what that BED folder looks like. Now we can see this is Sani tutorials, and we've just created this BED folder in the process. And now we have the log file, the BIM, BED, FAM. So we have these 4 files for a given chromosome here. We've got these 4. And for the 11 chromosomes, that leads to 44 files, 4 times 11. So we now have all of these. And so step 4 is done. And then what we will want to do now is we're going to want to gather all of these files together across these 11 chromosomes in our case. We want to gather them all together and stitch together all the BIM files into one, all the BED files into one, and all the FAM files into one. So that's where we want to merge the BED file. So one FAM file, one BIM file, and one BED file. And it's going to be easier, like for different applications, like when we're running the PGS calculator. It just makes it a little bit easier if we just have one file, I think, just it's easier to work with. So let's see how that works now in step 5 next. So the output files are a plink binary set. For each chromosome, it produces 3 linked files and a log file, a .bed, a binary genotype matrix. So a compact binary file storing genotype called 0, 1, 2 copies of the alternate allele. Rows are individuals, columns are variants. .bim is variant information, and .fam is sample/individual information, and the log file is the process that was run on DNAnexus, just for our reference. Together, these files form the standard Blink dataset that's widely used for genome-wide association studies, so GWAS, quality control, QC, and downstream genetic analyses, as we will be doing like polygenic risk score predictions. Yay! Welcome to the fam! So we went from BGEN to BED and fam and BIM files. So yay! Welcome to the fam. This is the new genotype information we're going to be working with. So an example BIM file here. So if we go to the extracted genotypes bed again for chromosome 2, this is the BIM file. So it's a tab delimited, so it's separated by /t, the tab separated text file with, chromosome 2, variant ID like the reference SNP ID, the genetic distance cm centimoigens, usually 0, the base pair position, allele 1, which is reference because we use ref first, that's what this is here, and allele 2, which is the alternate allele. This is an example of the .bim file. This is an example of a .fam file. So .fam, it has a sample and individual information. So one line per individual in our data. So one line corresponds to the given sample, like the given person. They don't have these headings on the top. I just added these in for reference. But this is the family ID here. And in my case, the family ID is the same as the individual ID. This is the paternal ID here, the PID. This is the maternal ID, MID. Here, these values are 1 if male, 2 if female, and 0 if missing, as you see in this column. And the -9 for phenotype means that it's missing and it's the default. And you might have seen in one of the log files that said like the phenotype data is missing. It's all good, don't worry about it. But this is an example of a .fam file, so about like the sample information, like family, paternal, maternal. That's what fam is, family. And so yes, you see here is an example of the log file for chromosome 2. It'll also be mentioning how long it took, and so on. No phenotype data present. All the stuff that's happened here in the log file. What was run? Options in effect. This BGEN, ref first, make bed, output, and the sample. So it's running them as a set of commands using Blink version 2.0. So we have the Blink 2 formatted genotype files here. These are all of the files. So we have 4 for each given chromosome. We have like 4. Yeah, like for chromosome 20, these are the 4. So you can see 4 for each of the 11 chromosomes that we have those score files for. Score information for needed. It's 4 times 11 chromosomes, so 44 items. It checks out. So this is where the files are all stored for the extracted genotype files. So for each of those 11 chromosomes, we've got the BIM, BED, and FAM files, as well as a log file for reference. And again, the reason we did this is the current input genotype file format supported for PGS-C calculator are the Blink 1 file set, the .bed, the .bim, and the .fam. That's how we did this conversion. So we moved from the BGEN to this format.